Welcome everyone on Zoom and in here. I'm filling in for Jonathan Chen today, who's on service. Today we have Jason Fries and Ethan Steinberg, research scientist, PhD student in computer science, talking to us about foundation models in healthcare. Without further ado, take it away.
Awesome. Thanks so much, Nigam. So Ethan and I will be co-presenting, so I'll do a handoff of the baton when we get to the work of most of Ethan's dissertation. So he's really been one of the student really driving a lot of the innovation here. So it's a pretty exciting space. So to start, why are we here? Really, it's because just over the past couple of months, generative AI has had this big breakout moment into the mainstream. Researchers have been working on cool stuff, but now we've reached this inflection point where a lot of different people are talking about how models like ChatGPT or large language models generally can really change the game when it comes to AI. This also surfaces a lot of these long-standing issues present in these types of models, such as hallucinations and all kinds of sort of potentially malicious behaviors that give people pause when you think about translating these types of technologies into healthcare or other societally critical situations. So the way we'll structure the talk today is we'll give a very lightweight language modeling 101 lesson to folks. Most people in this room will probably know how that operates. And then we'll go into some work led by Michael Warno and Crystal Zhao in our lab on the shaky foundations of medical foundation models, just the sort of sorry state that evaluation is currently when we think about these models. And then we'll segue into our research into foundation models using electronic health record data. And that will be comprised of Ethan's latest work, Motor, and then new work we're building in a language model we're calling Lumia. And then we'll wrap up with the road ahead and some challenges and opportunities and sort of our biased take on the world. And we'll get people's thoughts and opinions on where to go next. So language modeling 101. So at the heart of it, anyone who's ever taken an intro to NLP course should be very familiar with the idea of language modeling. Basically, we're modeling the probability of sequences. And so in the natural language land, you want to perhaps predict the next word in a sequence, given the words you've observed prior. And so how this translates mathematically is that you are basically representing this joint probability using the chain rule, where you can exactly rewrite the probability as these product of conditional probabilities, which is just a mathy way of saying predict a word given the previous word you've observed. So what's really changed in the past couple of years is, again, this is quite an old idea, but the models by which we can parameterize using this idea are much larger and much powerful now. So it sort of opens up this amazing new world of abilities when you can start estimating the probability of these things with some degree of reliability. And so the ingredients of kind of our modern era of language modeling are a lot of data, which we call pre-training data, a choice of a model architecture, which in our world is usually this thing called the transformer that came out of Google. It's a deep neural network. And then a massive amount of compute. This is on the order of millions of GPU hours, the kind of stuff that Google or supercomputers have at the ready. But these ingredients taken together allow you to train language models with billions of parameters. And the sort of interesting discovery of the past couple of years is that some kind of dumb scaling, the bitter lesson, if you're familiar with that opinion piece, is that scaling provides all of these sort of really interesting, amazing abilities. Google has this nice graphic showing about how a model, simply by scaling parameters and training data, suddenly gains all of these new abilities, which are called emergent properties. The things we didn't anticipate observing, but suddenly are now abilities the model can do. And there seems to be this kind of phase transition that happens as you scale these models up, where suddenly a model goes from not being able to do something and then being able to do something. And from that apparatus at the human level, we now have this really elegant framework by which human AI interaction can take place using natural language, both as an input and then an output. And then also under the hood, you generate these numerical representations of the language you're using or the things you're asking questions about, which are also useful for AI purposes downstream. And so language models are an instance of this growing class of models, an idea that's been advocated by Percy Liang's group and collaborators on campus as foundation models.
When you say language models, you mean specifically deep neural networks and transformer architecture?
I mean, the model I opened the slide with, predicting the probability of a sequence, the joint probability.
Other approaches to language processing. I just want to be
Yes,
clear.
that's
there
a narrow
are-
description.
There are other approaches.
Of course, yeah, of course. The benefit, of course, is that these are extremely generalist models. So older methods can sometimes be subsumed by the abilities of these models. And what we're finding is that you can take these ideas to domains that are not language. For example, imaging, waveforms for language, all kinds of different modalities can fundamentally be represented as a sequence of tokens. And this way of sort of training a really generalist model then gives us the ability to adapt it to a wide variety of downstream tasks, which is really the kind of magic of these things, is that they're able to do so many flexible behaviors without really sort of baking that in, which we kind of had to do with the older methods. So this idea is exciting. It's excited a lot of people. It's certainly excited folks in our lab. And we sort of kind of buy into this a bit, advocated by the economists they like quite a bit, that foundation models are moving AI into their industrial age, where we can now envision a future where we ingest highly heterogeneous multimodal data and build a generalist model under the hood that is now suddenly capable of doing a wide variety of different tasks. And by sort of collapsing everything into this sort of single idea of an interface or representation, you open up these really interesting ways of interacting and doing anything with these big models. And so, you know, that's all exciting, but when the rubber hits the road, if you actually look at sort of how the current generation of these models actually behaves, if you kind of ignore the hype, you find that it's on pretty shaky foundations. And so we did this, we have a couple opinion pieces, blogs out on the HAI blog that really kind of talk about opportunities for foundation models, and then also just the kind of sorry state of affairs when it comes to assessing these models' utility, fairness, and actual you know, benefit to a healthcare system. And kind of where we're coming from and is, you know, there are multiple axes upon which you can assess success taking any AI into sort of an institution, be that a business, be that a healthcare institution. But the current state of affairs is to very narrowly evaluate on things like better accuracy, sometimes sample efficiency, that's using less data, but often things about impact on downstream workflows, impact on the cost, or this, you know, practical ground level performance of keeping these models deployed. We have no sense of what the hidden costs of those are. And so we kind of proposed this maybe richer set of evaluation axes upon which you could think about models. And then
You're suggesting we need more than one metric?
correct. So the view of the world here that we kind of take in this position piece, this is work led by Michael Werno and some other folks on the team, is you can think of the world of medical foundation models, language models, into two categories. Those that consume text, which we call CLAMs, just for a shorthand. They take in clinical documentation, they may generate more text, or they may be used in some capacity for a prediction task, like by generating an embedding. But there's this other class of models that take in, you know, a single document is a very narrow perspective on a patient state. We, in fact, if we do analysis with healthcare data, we often look at longitudinal data, we look at the person's health state over time, we get a lot richer perspective. So we want to ingest entire timelines of a patient and use those to generate an embedded representation for prediction tasks. And we call these models femurs, which are foundation models for electronic health records. And if you are to look at the state of both of these classes of models, you will find they're quite divergent, even though they both nominally live under the healthcare umbrella. So language models, during the moment we live in, are much more popular. There are 51 of these things out there that are connected to clinical text in some capacity. This means they were trained on mimic data. They were evaluated sometimes on clinical language tasks, like pulling diseases out of notes, let's say. But they very narrowly focus on accuracy, and they very narrowly focus on these sort of core classic NLP type tasks, which are pretty far removed from the day-to-day, activities of a doctor or someone trying to do their business of taking care of patients. If you look at femurs, there are less of these published, only 29. You'll find that they do slightly more clinically meaningful tasks, things like predicting mortality, maybe predicting sepsis, things that like Epic might have implemented in the EHR system. But you'll find that these types of models are very different in terms of our ability to understand how well they actually perform if we were to take these into a hospital. And if you just break things down into sort of two views, you find that on the clinical language model side, the majority of them are public to researchers in some capacity. This would be 36 of 41, 51, excuse me. But if you look at the femur class, which has a huge capacity to represent patient state and do patient level predictions, only 3 of those models are available. And those are actually quite old, right? So we have no ability to interrogate the performance of these models, to say nothing of the fact that we have a huge data set benchmark problem in healthcare more generally. And now we've transitioned to a land where we also have to think about assessing a model as an artifact. And so now we have 2 free variables upon which we're just stumbling in the dark to not know really what guidance we should do for what we should pick and choose to move forward. And both of these are evaluated on different tasks that are largely disjoint and are often different across papers. They don't evaluate on the same data sets. So there's really no ability to draw strong conclusions about anything, unlike generic language model land, particularly like the work out of Percy Liang's lab, where they've taken a holistic view, where they say we want to assess models over multiple dimensions and keep everything fair and the same. And we want to benchmark and really know, kicking the tires, how these models compare to each other. And then, we also, they benefit from a lot of tasks that do have meaning to that community. In healthcare, we have a lot of, fog of war of understanding applications that are clinically useful in the hospital, just partly or largely, you could argue, due to barriers of ever even getting a model deployed and in front of clinicians. It's so hard to do that we haven't had this iterative process of finding the good applications that are worth optimizing, that are worth benchmarking. So we have this gap where we have on sort of the state of now on the left, which is NLP focused, heavy on sort of like, off-the-shelf benchmarks with unclear utility, and perhaps this sort of recent flavor of new NLP tasks of, getting GPT-4 class models to do cool stuff. But that's a pretty wide gulf between improving outcomes for patients, reducing costs for the hospital, really improving lives in any meaningful way. And what we desperately need is to bridge that gap with, expert medical knowledge, real patient data. Most of these models never see real hospital data, and legitimate technical innovation for how we adapt the general domain stuff to our healthcare setting. So with that, we will segue into our lab's work on EMR foundation models. So just for on high, this again is probably for this audience very well known. Electronic medical record is a collection of different types of data. This can be things like structured data, medical codes, might be things like lab results. It can include clinical notes, that's unstructured data about some patient encounter. Increasingly, we can think of all kinds of exotic data that may show up in the model, like genomic sequencing, wearable signal, all kinds of really interesting multimodal data. In principle, you could think could be used in some way to maybe inform patient medical decision making. And so if you were to kind of bucket potential uses of AI for healthcare using EMR data, this is sort of my very CS kind of breakdown of the world, which is in some cases we're concerned about a patient and what happened in the past. This might be things like summarization of a chart or a medical record. It might be for constructing cohorts for research questions. We have the data there, it's just sort of finding the gold and the needle in the haystack. And data is very messy, and this is a non-trivial enterprise given the high level of noise and incompleteness present in medical data. You might have what is occurring now. This might be stuff like your class of radiology models. They're handling diagnostic actions, such as predicting presence or absence of clots in PE. You may want to identify cancerous cells in a pathology slide. And then we also want to be able to predict future risks and intervention benefits. What patient will develop nephritis, who will develop chronic pulmonary hypertension. When to marshal the evidence we have about a patient, be able to understand where they may end up to guide our treatment decisions. And then this, of course, is all situated in situ at the hospital, where we have to make a bigger decision about whether to treat, how to treat, subject to all the realities present in policy, capacity constraints, and the limits, of the intervention itself. So with that, I will transition to Ethan and how he is using EHR data from Stanford, which is called STAR-OMOP, in his research to build models for this domain.
So the key insight here is we can view we have sort of like an EMR language of codes that can be viewed similar to like a natural language. So on the bottom, I have an example, take patient, we have a list of visits, each coded. And similar to how you might have you have patterns in English language, you have patterns in the coded language as well. For instance, that patient at the bottom has a diabetes diagnosis. You probably expect they're going to have some insulin codes in the future or possibly diabetes complications. And because we can view the EHR code set as sort of like a language, or a sequence of codes, we can apply very similar techniques, what is used in natural language, to our coded data. And this enables us to do self-supervised learning. Like a large unlabeled patient population. We can do pre-training on that through the language model objective of predicting future codes given prior codes, develop a foundation model on our coded data, and then adapt that model or generate representations using that model for a small labeled set that's much larger than our general set. And the core assumption here is that there's like some shared structure between the two. For instance, let's say you have a target task like ER patients. There's some shared structure like the ER patients or your inpatients. And so there's going to be some value there transferring from the larger population of patients to just patients in the ER. So in one of those, for this work, we're only focusing on within Stanford transfer. There are theoretical proposals to like do between hospital transfers. You can train like a very large hospital and transfer to a smaller hospital. But for this work, we're just focusing on in a single hospital institution.
Could you review self-supervised learning?
Self-supervised learning is when you're predicting and you're trying to predict the data itself, or predict an attribute of the data itself. So for language, we're going to go into explicitly what I mean by that. Yeah. So our first step with this is Climber, which is sort of an autoregressive structured EHR model, where the self-supervised learning in this case is predicting the set of future codes given all of prior history. We construct an autoregressive objective to do sort of like set-based learning. And take advantage of knowledge graphs to sort of like when we're predicting a set, we can pick the set in sort of a knowledge graph oriented way. Then we can use either an RNN, like a standard GRU, or a transformer backbone to do that prediction, to do that training, and self-supervise in all Stanford data. And this generally works pretty well. We can see about a 3.5 to 19% improvement in binary task AURC. We can also see that our classifiers decay less as time passes. Mainly because we're pre-training. Area under their super operator curve. I got used to the questions, right? Because defense coming soon. Anyways, so we also find that classifiers transfer better across subgroups, mainly because you know that huge body of patients you were able to pre-train on. So it's much more robust model. The main issue with Climber, the one that we found, doesn't do as well for like time event tasks or other situations. That's why we have these two additional efforts, Motor and Lumia. Motor is many outcome timeline representations, and it's specifically designed to generate a foundation model for timed event tasks. And so we're able to get pretty good improvements, time to event tasks, similar to what we saw with binary tasks, with much faster training than baselines and also much less data than baselines.
Looks like you guys used decoder part only, right, in the previous slide? But it's more like a classification test, right?
Well, sorry, this gets into the details of how like transformers and RNNs are set up. From a transformer perspective, this is usually called a transformer decoder. I'll get into what the details of how exactly the transformer details later, but that's sort of the name of it. Yeah. But yes, after that, you just do normal classification. Use the general for climber. Use just linear regression model.
No, I was wondering why you picked decoder part over encoder.
I'll get into that very shortly.
What are you referring to as a time to event task? A prediction?
Predicting the time until an event happens.
Okay,
I'll,
so the task is predicted.
yeah. These are all climber and motor are both designed only for prediction tasks.
Okay.
Climber is designed for binary predictions, predicting like probability a patient's going to have something. Motor is trying to get you the exact time when they'll happen, or very rough estimate of time. Emphasis on rough. And final effort is Lumia, which is a language understanding for medical insights and action, which Jason's leading, which is basically more focusing on like text generation. We get a foundation model that predict text very well. So the fundamental question here, the problem we're trying to solve is how can we better predict time to event tasks? So for time to event tasks, the sort of examples like on the right, we have patients, we have probabilities of survival across time. We're trying to generate these curves for each individual patient in our data set for a particular like task definition. Why is it important? I mean, why are we focusing on this? It's hard for existing techniques, mainly because it's very parameter intensive. You're trying to estimate a whole like sort of survival curve. Also, it's very important clinical applications. Knowing someone's going to have cancer is not very useful because everyone's getting cancer eventually. You need to know if they're at high risk cancer and soon. So we have a proposal, motors, or all this. So this is the overall design, and we'll go through each component. The main idea is will be like a pre-training task setup, which is the top right. So like predicting all these, we're predicting many tasks. We have a neural network transformer to actually do the modeling, and then we have to refit our models to do a particular target task of interest. So the key difference here between motor and prior work is we have this new time to event pre-training task. Basically, what we do is we look through our entire medical records data set. We find the 8,192 highest entropy codes, and then predict time to event for every single one of those codes, every single time point on all our patients.
Sorry, excuse me, do you mean highest entropy like CPT code?
I mean entropy in the like information sense, which if we compute an entropy, so if you compute the entropy like the probability of the code times like the frequency of the code, yeah, that's something the highest entropy, like in information theoretical sense.
And okay, of the codes for the patients.
Yes.
Okay.
And the codes are, when I talk about codes, I generally mean either ICD codes,
Right.
CBT codes, HCPS codes, LOINC codes, the drug codes. I think we're using ATC. Those are the main categories, I believe.
Right, and so you're ranking them by their predicted or their like calculated entropy.
Yes,
Cool,
that's why we select our 8,992 tasks.
nice.
You describe the index time for this, which is like the time from first diagnosis or like time from first visit.
This is the time until the first, so the index time, we're doing the same time of prediction at every single time point. So the index time is every point on the patient's timeline. The target time is the time until the first occurrence, or sorry, the time until the next occurrence of the code. We have a relatively simple neural network architecture for generating representations, which is the intermediate step of this. The main steps are we have to convert our codes to tokens. We just do that in a straightforward manner, create like embedding for each code in the data set. We have to use it. This is where it goes into like the question, like a decoder, it's also called a causally matched transformer. What that basically means is that you only allow information to flow forwards in time. You don't allow backwards connection to a neural network. So let's say at this particular time point, you don't allow this RX norm code to like, there's no path of information flow from this RX norm to this point in the time point. That's necessary because otherwise the prediction is trivial, right? If you could use your future information, predicting like the code that you already know in the future is trivial. Second aspect is one difference between EHR records and like documents is we have a very complicated notion of time, or at least a very like a sort of well, not really nonlinear, but we have times per tokens. And so we use like rotational embeddings to enable that time information. where we denote time usually by days since patient birth. And so that's what those numbers there are, days since patient birth. Most of which are pretty large, because most of our patients are pretty old. Most patients have a lot of events are old. After this, we can pull embeddings off the last layer of that transformer. Just pull them off right off the last layer. And these embeddings are fixed dimension, I think they're like 5, 12 dimension, just vectors for every single time point in the patient. We can then use this to construct a piecewise exponential time event model, which will actually predict these like curves. We use the piecewise exponential models are quite simple and pretty good for deep learning because they have very simple law. They have very simple like function of the hazard as a function of time. Usually bin time into discrete segments. And then you have the hazard be a log function of the features at that time point. So this is like a 3-bin model. Each dot here represents a time point that we're saying the hazard changes at. And so we compute this log hazard at each of these little individual time points. So then for transferring to a target task, it's somewhat similar to our pre-training setup. We extract our patient representations. We extract our little blue boxes, which are like 5, 12 dimension vectors. Then we refit a piecewise exponential model with regularization. For pre-training, we don't use regularization because we have tons of data. But for our target task, we have a lot less data. So we have to use some regularization. We also have to use a careful optimizer because these are difficult models to fit because they're sort of actually doubly exponential. Because like the log hazard is a function of the features, but the actual probabilities are exponential of the hazard. So they're a little difficult to fit, but they are still linear models or sort of linear models. The result is we have these nice little survival curves for each patient that tell you the probability until or not having a certain event. This is an example of 4 random patients from our data set.
So what's happening here, just to make sure I understand? You're using a lot of historical data to create your model?
Yeah,
or are you some, and then you're applying that model to particular patients' data, but sort of in a typical predictive machine learning mode?
So we fit our foundation model with all Stanford's data. We use that to generate representations for every single patient. And then we have like a target task, like a set of things we actually care about. We pull those representations and then just train this little like this piecewise exponential model on those representations.
But you don't do that separately for each patient. You do that for all patients for that task.
Yes.
The key
Yeah,
to
that's what I meant.
understand here is that, and we do have a test set, so these people have never been seen by the model. It's an important distinction. So there is insufficient data for any single time to event task to learn a good model or to learn the most performant model we could. And so the intuition Ethan is applying is that, well, we can leverage every time to event task in the entire hospital to train a single model, which is then much more proficient at estimating time to event curves. We'll take that model and adapt it to a dramatically smaller set of interests. Could be 1 patient, could be 1 million, probably usually like 10,000 or something. And that model will be wildly more performant than if we just started with the 10,000.
And this is different from classic work on multicast, where you would simultaneously train.
No, it's actually quite related,
I
right?
think it is related, but it's
Yeah.
not quite the same, because you build it in a semi-supervised way, and then you train a separate predictor for each of them. As multitask learning, you would do them all at once.
Well, the pre-training objective is multitask learning, which is sort of the dominant paradigm now. In text, that's a little hidden, right? Because text is like unclear. But with codes, where you sort of map to categories, it's much clearer. That is multitask. And then the adaptation could be multitask, but it's often binary in our setup.
Yeah, you could in theory also like fine tune the entire model on your target task and it would be a true multitask setup. That's generally not worth effort because usually your target task is too small relative to everything else. So it's just there's not enough signal there to be worth it. So how well does this actually do? Like sort of the number that we can actually measure. We construct 6 time event tasks predicting the first occurrence after your history at a random visit. So this is when we actually get to the definition of like what is our actual index time here. So we require your history, we select a random visit after your history, and then predict the time until the first occurrence of one of these various things, each of which are defined by a set of IC9 and IC10 codes. The sort of selected just be sort of a random selection of both sort of chronic and also more like acute conditions. We compare a bunch of models. We have a standard Cox model. We have deep serve, which is a straightforward like deep learning approach. RSF. We have motor without pre-training. So this is if you throw away the pre-training, you throw away the time demand pre-training and just use the model by itself. And we also have the motor, which is when you do the pre-training and you also fine tunes. And so we evaluate all these on the time dependency statistic, which is sort of a very similar to ARC. The intuitive explanation of this is it's the probability that you will correctly rank one patient over another. In terms of like you say their hazards are if you say a patient has a higher hazard than another, that person will have an advantage sooner than another patient. It's a very complicated metric, but it sort of gets what we're trying to get. And you can see we get pretty impressive performance, much better than all of our baselines, as well as over just a non-fine tuning whatsoever. And the benefits generalize across many of the time horizons. So that bottom is where we bucket the time horizon in. And we can see that our ability to rank patients is improved at basically every time bin, although the improvement decreases at later time bins. It probably reflects how, once you start predicting like a year in the future or like 2 years in the future, like from the informational perspective, theoretical perspective, there's not really too much you can do from at that point, so.
What are the time bins? Like what's the maximum time?
It depends on a per task basis, but generally about 1.5 years for the maximum task, for the maximum bin. It depends on the distribution of times. These are percentile bins, so it's the percentiles of the actual event times in our data set. We also have greatly improved sample efficiency. So here we can see where this is just a subset of the previous plot. We're comparing RSF, which is only the strongest baseline. And here we compare motor, but we fine tune on a much smaller data set. So the first row, we only use 5% of our actual labels for fine tuning. And you're able to get pretty good performance, even with a very tiny amount of data. The reason why is because these are like heavy. This is a very simple linear model, only has 500 parameters. So you don't need that many patients to fit a 500 parameter model. Or 512 parameters.
All right, thanks, Ethan. So to transition a little bit, so where we started with femurs and clams, clinical language models and structured foundation models, if you look at the EHR, you know that neither resource in isolation tells you everything you often need to know. That's in general with the whole EHR, but there's tends to be siloing. There are things that are only available in notes, the things that are only available in codes, clearly or easily accessible. And so, we've been really interested in how we can make language models of the GPT style more useful in clinical documentation settings. And so what we've been exploring is this model we call Lumia, which is language understanding for medical insights and action. And instead of taking the classic perspective on language models, no worries, where you focus only on documents, that is like a single narrow slice on a patient's time in the hospital, we transitioned to timeline. Yeah.
Sorry, just from the beginning, when you talked about clams, a question I've had is, are most of the work being done with clams really looking at single documents from one sort of time point, where they are not incorporating information about temporal order of existence of those documents? They're just trained on a whole set of a bag of documents. Yep. So is that something worth investigating, do you think, if you?
That is what we're investigating. That is the timeline perspective.
But using both structured data and notes, right? Or are you going to show results on when you take that approach and look, only at?
Well, there are no results. The model's training. That's sort of like.
Is that a plan that okay.
Correct. Yes.
Thanks.
So like Allison said, a lot of clinical language models just consider the document processing component. They're not really interested in patient state, as it were. And so the hypothesis is that, well, does that matter, right? And so if you both situate multiple documents and codes together in a language model formulation, can you do better for both language tasks and patient classification tasks? That's the core hypothesis. The limitation here historically, if you look at, say, like off-the-shelf models like Clinical BERT, they only consume 128 tokens. That's not enough to fit even a single document, let alone an entire patient history. But if you're familiar with work that's going on in computer science, like in Chris Ray's lab or like GPT-4 now, the effective context width, which you can think of as an analog to memory in a computer, is dramatically increasing. So our ability to just gone to 8,000 tokens, now 32,000 tokens in the most state-of-the-art model, Chris's model, his lab's model, can theoretically has no context width. It can in theory take hundreds of thousands of tokens. So our universe is like, what if we can now not only condition on the entirety of a patient record, but could you imagine the entirety of all patients' records to be able to do in context learning or these really amazing sort of like uses of big language models. And so it's all kind of predicated on how well this idea of like, well, if you pack everything into text, how well does that actually work? And so that's where we're starting. We're combining notes and structured data. We're training on a much larger base model, which is already 8 times longer than the longest public clinical language model. We're sort of teed up to evaluate a much larger context model when it's implemented. And we're training a 1.6 billion parameter language model over these data. This is probably 3 times larger than the largest publicly available clinical language model. And it's at the phase transition point where you will expect something called instruction tuning, which we'll talk a little bit about in a sec, to actually start being impactful, which means we can take this checkpoint and adapt it to the instructions, say, a clinician actually generates and suit it to perhaps do better for the types of tasks you may want to do in the hospital. So as I said, with the sort of bearing the lead here is that we don't have numbers yet because of the model's training. Sort of these models can take a long time to prepare data for and to train. We are evaluating, we've put together a sort of longitudinal, or sorry, a wide breadth of different task data, including samples from classic NLP stuff, where we sort of cover what most language models are currently evaluated on, including stuff like MedPalm. We've also incorporated patient classification tasks. These are things that people have done, like, mortality prediction or readmission using notes. That is actually, there's a little bit of prior work. It's just hard to evaluate its efficacy for the reasons I opened with. And then working with clinicians to find a series of tasks tailored to star OMOP data that might have more clinical plausible utility. And it's all sort of curating that and packaging it together in a setup, sort of like as a baby 1.0 version of Helm, in which we can release this to the community, and future language models, ours and hopefully others, can evaluate on the same thing with all of the same assumptions and start actually making claims about how well these compare against each other. All right, so the road ahead. The favorite comment on GPUs is that you're just contributing to melting the icebergs in addition to burning money. So this is the point of this graphic. For if you pay attention to this field, it's basically insanely breakneck, crazy pants pace. And it's absolutely almost impossible to like take a week off to get work done and then you come back and something that like turns the table upside down on you. And so there was a work a month or so ago out of the CS side called Alpaca. They found that you could actually replicate the original performance of GPT-3 for on the order of $600 by using GPT itself to generate an instruction tuning data set for you. And so this has been the first of now many, especially out of like Databricks, where they've released an open language model called Dolly, named after the cloned sheep, and built a data set of like no commercial restricted instruction tuning over like 2 or 3 weeks using all of the folks at Databricks to generate instruction data for folks. And this is on a model you can now like fine tune on the order of a couple $100. Microsoft has released DeepSeed, which is you can train even like fine tune even 175 billion parameter model. That's the biggest that we ever knew about GPT-3, for like a couple $1,000s. So this landscape is dramatically changing.
Cost of training or cost of using?
Cost of training. Using that's another. Using has its own additional costs, which should be measured and assessed. It is one reason why it is probably for an institution much cheaper to cook your own model up and use it internally than pay Microsoft. There's also business concerns around like data moats. Like, do you really want to give your data to Microsoft OpenAI so they can learn from it? Or is that something you should keep internal to the company or to protect your patients? So what we're seeing is this landscape now where we can kind of align these giant commodified open models to domain-specific use cases. And we start from like these giant public checkpoints where we've amortized the cost of the heavy lifting to get the initial model. And then we adapt it to our specialized domain using these self-supervised objectives for text, like Ethan talked a little bit about. And then now we have this new knob that is really the secret sauce to aligning the behavior of these models with how humans might want to use them, called instruction tuning. And so what we're transitioning now as researchers and experts in fields is how do you build instruction tuning data sets cheaper, faster, and in ways that diminish hallucination, tabulations, all the other problems that we encounter with language models, in addition to legitimate technical innovations with how we train these things. So the reason I harp on open models is just this anecdote from GPT-4 and just how nefarious it is to take the stance that you will share nothing about the model, including what it was trained on. And so we know that it stopped training on 2021. You see these amazing numbers about GPT-4 being able to pass coding exams and do all these kind of crazy things. But if you actually do an assessment of like data, like questions the model could plausibly have never seen, like it was never in its training data, the performance goes from perfect, like superhuman, to terrible. It gets nothing right, right? So this should give you incredible pause about how these models are actually utilizing the information they learn from the web, and put you extremely skeptical of claims of companies that release nothing about how the model was built.
Like reading the fine print there, it looks like one of those 2022 questions is it a cat?
I'm sorry, what's that?
The second question,
Oh, I
is it
can't
a
actually
cat?
see it.
Yeah, it's just the name of the question, that's fine.
Yeah.
These are programming questions, so
Uh-huh.
these aren't like,
Uh-huh.
like here's a picture of a cat. I don't know what that is. That would be.
I'm like,
yeah.
what? There's no cats pre-2021 internet? There's
Yeah.
no way.
No, it's a very narrow, goofy CS, like trick you, lead coder kind of question to
Uh-huh.
prepare for technical interviews.
Uh-huh.
And so it's probably something about flipping a string around or whatever, I don't know. But anyway, so
Problems.
Uh-huh.
yeah, and this is even more nefarious when you think about like Microsoft is bringing online things like retrieval, right? Where you can fetch fresh information and contextual and condition or ground on recent data. But they've done research that even like there's something about the model weight memory that even if you condition on recent memory, you still do wildly worse, right? So it's you just need to know what was in the training data, and it provides very few guarantees, even when you build in stuff like, augmentation with retrieval engines and other safety mechanisms.
So there's
Yeah.
sort of two questions from the online
Yeah.
audience that are sort of technical. One is, what is the best way to control for overfitting in this type of a model? I think it's for the Lumia model. What methods used to calculate sample size of the test set? Maybe it's for motor.
Yeah, it might be for motor. I
Yeah.
think there's, yeah.
In order for the foundation, the core foundation model, where you're training on the 8,000 tasks, overfitting is not too much of an issue, mainly because there's so much data there, it's hard to overfit. We do have some regularization, but I don't think it actually does too much. I mean, you control for overfitting the way you have to control for anything in any model. You have a test set.
Smaller training set, you'll get overfitting. So you're really talking about the relationship between how much data you have and.
Yes. But in principle, if you were to see it, you would see it in our validation logs. If the validation loss goes up, then that might be an issue. that you can
Yeah,
remove.
then there definitely is a slippery notion of overfitting now as we think about like smaller, more sample efficient models, right? Because the samples you choose to, even though it's smaller, now you have this additional level of variation from that choice. And so it's entirely possible to select the wrong few shot examples and like actually do worse with the model. So that's why there's legitimate research around like how you pick good exemplars, even in a few shot setting. But there's training and that we've decomposed this pipeline of multiple steps now where problems can creep up. So yeah.
I think there's also a sub-question about the test set size.
Yeah, there's another, so related question was, what's the method used to calculate sample size of the testing set?
So for the motor paper, we use patient splitting. So patients are split into train, validation, and test. So the size of the test set is simply the number of patients in the test set, which in our case was 15% of the Stanford patients.
Right, and then the second question I think is, most likely with Lumia, are the clinical notes and aren't the clinical notes and medical codes correlated? Would it introduce bias?
They're certainly related, and there certainly is like, I think bias is a really interesting question because certain things are coded and certain things are not. And so I think text may actually mitigate bias if you use it to generate representation that uses both. But it's a fair question that I don't have a good answer for, like characterizing that as an interesting direction.
Yeah, and then final one, more of a helpful suggestion kind of question. Could a structured encoded medical knowledge base be used to facilitate supervised learning or to assess the veracity of the output?
Oh, yeah, absolutely. Yeah, totally. I mean, I think like there's this universe now where we're using models to train other models, right? And so I think there's this other idea of like, these are so flexible, they can be integrated into many aspects of what we classically think as data science. And those plugging into all kinds of places is really exciting, right? As we learn new abilities of how these can check assumptions, look for errors, look for noise.
Yeah. So just a process check, we're 13 minutes out from 1 p.m. How many?
Like one slide.
All right, then we'll take other questions after that. Go ahead.
All right, and so just to wrap up, two directions I see sort of really promising moving forward is we really need to dramatically rethink evaluation, right? Like even our current paradigm of seeing how well a model passes a USMLE kind of exam or the bar exam is fundamentally flawed from a construct validity perspective. That's not the right way to assess how well a model will work in situ in the hospital. It's not the right way to assess how a model will work with humans. It leans into what a model is good at doing, which is retrieving facts efficiently. We need to think about how that model works in the context of a human and how they work together synergistically to accelerate and improve their performance. And we don't do a good job of doing that for totally valid reasons, right? Like it's really hard to get a model in front of people. It's really hard to bring humans into the loop, especially as computer scientists are very used to just like spinning something up on a data set. But we really need to think about these sort of like, real world studies with humans doing their jobs to actually sort of think about how these will change things. Yeah.
And maybe you shouldn't report area under the ROC curve, but rather look at the cost of the types of areas.
I think you should report a lot of things, right? I think it's reporting any
But not
single
just
one.
that.
Yeah, I think that's a shorthand that is perhaps leaned on too much, but you're right. More metrics, which 100% agree with. And then close to my heart is the idea of data-centric AI, is that we know sort of we're hitting the limits of just scaling with data. In fact, if you believe chinchilla scaling laws, which came out of Google, there aren't enough written documents on Earth or in human history to train the models of the sizes we could conceive of working with. And so we really need to start moving from dumb, big engineering efforts to sort of thinking about how the data itself may be curated or constructed with domain experts injecting information, how these things can, when a 2% error drop in error rate comes at an order of magnitude more cost than data, compute and energy, that is not a sustainable path. And it's also, a path that really has to involve researchers and experts. Like you can't just engineer your way out of that hole, I think. And that's it. I just want to thank a huge number of people who have been involved with various pieces of this project. So it crosses multiple teams in CS, multiple labs, and a lot of like really great people in Nigam's lab, and then collaborators from other institutions. And this is all like a big effort to really start, kicking the tires of this idea of could we start really seeing these type of models work at other places and other hospitals. So with that, thank you so much. All right.
Could you just clarify what you mean by foundation models? Does it have to be a deep neural network, or can it be anything that is based on a large corpus?
Well, I think it's a fair question. In our current moment, it's a neural network because that's the most effective to accomplish those aims. Could something else replace it? I certainly hope so, but not at the moment.
I mean, you go back, the Psych project was sort of trying to get at that by manual knowledge engineering. Would that, in principle, have counted if it?
I don't think so. I think anything
Because it has to be learned?
has to be learned and has to scale. I think scale and not in the generalist component. I think
You just said that this stuff doesn't scale.
this,
So which is it?
What do you mean doesn't scale? Sorry, what did I say doesn't scale?
You just said we're running, it's going to stop.
Well, so the data, so I should clarify, our ability to get continued gains
Okay.
will reach a limit, right?
Right.
That doesn't mean this amazing thing that crushes everything that's come before
No, I know.
can't be continued to be
But the-
tuned.
But the
Yeah.
same was true at one point for knowledge-based, handcrafted systems, right? So they scaled for a while and then they stopped.
Sure.
So I'm trying to understand in principle your definition. And so you don't object in principle to other approaches. It's just that there's one that is very popular these days.
Yeah,
Good.
I mean, like all things, there's a better thing around the corner, right? So,
All right, one question online. What are the different ways one can address issues of trust, explaining the clinical predictions made by the model?
yeah, that's like one of the big questions, right? Like, I think to some degree, we're just accepting to be fooled by this very glib output of these models. I think some degree of trust can certainly come in from just explaining in a capacity that's kind of aligned. I use explaining, that's a fraught word in its own right, but like decomposing the steps of a decision-making process so that in principle, a human could track those steps. That doesn't mean it won't lie and imagine stuff and hallucinate stuff, but at least that gives a human the opportunity to surface where it derailed. And I think that's as a first approach. There's this idea called the chain of thought prompting in the prompt engineering land that does give you a little more inspectability is my preferred word over explainability. You can watch sort of pieces of the model and you as a human sort of say, whoa, I don't think this is a reasonable thing and bail out. I think those guardrails are the most important thing to build into foundation models. Yeah.
When you've been having conversations about evaluation of the output of these models with people like Lillian and co, what are the types of errors or hallucinations that you think are the most important to look out for when evaluating something like Motor or something like Lumia that's trained on patient data? It's a little harder to detect something like a fake paper citation because that's not going to be what's output by those models. It's going to be something like a probability of a disease and so how do you?
Yeah, go ahead, please, yeah.
So the main failure case for Motor and Climber, so these sort of code-based models, is not really hallucinations. It's more about input ETLs and code data and transformations being correct. Junk in, junk out. So it's the same issues you'd use to debug any sort of like observational study relying on coded data. Like double check that, like do chart reviews, make sure that your data source actually matches reality.
I mean, Motor and Climber are like the black boxiest of black box models, right? Like EHR data is pretty hard to start. You saw the data, it's kind of a black box, right?
Yeah.
So it's even worse in some degree. And so figuring out a way to build in guardrails is a research question. I do not know. I think we have sort of like really like one layer of thinking about these things is like, could a PhD student figure it out? There are a lot of smart PhD students. Usually they can figure it out. We don't have PhD students for every problem that we need to solve. Can like a expert figure it out? Like we aren't at that level yet, right? We don't at a level where a doctor could look at a model, have the guardrails to sort of know that this is not to be trusted. And how to do that, I think, is a great area to focus on. And I think there's some opportunity in combining language models and these code-based models, because it gives you some ability for, at least generating something a human can look at more effectively than do a data analysis. So yeah.
Yeah, there's work I've been told going on with the OpenAI models on outputting an uncertainty around their answer.
Yes. Yeah.
That could be one way of informing an expert that, whatever output they're looking at is on shaky ground.
Yeah, definitely. I think stuff like that is worthwhile. There's like a fundamental cynicism of like asking anyone to put a number to something. So I think that is challenging in its own right, but I think that's the direction we want to go.
But earlier you said an interesting point about metrics, when you were describing the metrics of one of the studies you did, and you essentially said, Ethan said, it's a very complicated metric. I can't explain it to you right now.
Yeah.
I can't even tell you, I can't even relate it to anything that you already know about. So when your metric is something like that, what's the effect of that on convincing people that?
Yeah, 100%, right?
This is effective if you can't even explain what the metric
there's,
what
you know,
you're
sometimes
saying
there's
is
an
affecting
audience
me.
mismatch thing, right? Like, you know, Ethan could sit down and whiteboard out the explanation, and like statisticians like Crystal, who was a co-author, they would be like, yes, this makes
Right, but that
sense.
was on the
But
users.
yeah, exactly. And that's that PhD user, that's probably the better word, right? That gap is really problematic, I think, with these crazy.
I mean, we have problems for, if their user community is really clinicians, just really at the limit, an understanding of things like positive predictive value versus sensitivity and specificity. There isn't universal understanding of that, which are, eons simpler than
Totally,
whatever your metric is that you'd have to
Yeah, I mean,
whiteboard out to
I
explain.
think
to
it's like, nose to the page researchers, sometimes we do a little shadow boxing with like metrics that don't climb out of the silo we're living in. And I think you bring up a good point, is like, how do you, building trust is, metrics are probably insufficient in their current form in some way, because it requires some understanding that you can't assume of people.
So a couple of things. We have 3 more minutes left. There's 2 questions online that I want to get to, and then the questions of, evaluation paradigms. You might want to mention Dave's experiment and the blog, which is a way of evaluating how well these, without having, with metrics that people understand.
Yeah, I forgot to add, there's a third blog position piece with like Eric Horowitz and Nigam and Deb Dash, one of the clinicians. It's really good. It talks about these kind of questions too. So it's worth reading.
Now, there are 2 questions online. What are the plans for user interface of these models for end users? And this person asking about 2 use cases within Stanford where they could provide clinicians with access to previous patterns of decisions, or have a internet available site where anybody can search. So your thoughts on that? I'll give you the second question already. That's about, is there an information theoretic measure like entropy for sufficiency of an LLM?
Yeah, second one, I'd say no. Yeah,
This is a short answer.
They'll out there. Yeah, I mean, yeah. So the first question though, like making these models accessible, I think that's a huge differentiator. Is just exposing these to other people, especially the femur class models. Our hope is to release these in Hugging Face style, if folks are familiar with what that is. But it's sort of this model hub where researchers or permitted people can download the weights, and there's some infrastructure in place where they can play around with stuff. And you build trust by letting other people try to break your model and find out what you did wrong. And so that's one huge way to make them available. I think internally at Stanford, we're doing a big effort to try to build these tools in a way where you can continue to do rigorous silence if you respect like patient splits and our time splits and all that stuff. And so you can take these models internally off the shelf and sort of use them for your purposes in a way that accelerates your own research. We're planning to have workshops to sort of bring people in to show you how to use those tools. That's, a couple months down the road, but I think that's the answer there.
All right. Last question.
In the model system, as far as I understand, you created a pre-trained models in EHR, and so apply this pre-trained model to the classification to time to events task. I was wondering, when you created this pre-trained model, or the test sets patients have been included in creating these pre-trained models or not included?
Not included. It's a global 15% patient test split. So an entire, like every step of the process, 50% patients excluded from everything.
And how do you determine the positional, use only the positional vectors? And so how do you determine these positional vectors? Because in some cases, it's difficult to determine position of some text. It's not a sequential manner always, because, for example, one concept and next to this concept. And so some of the concept on the parallel. And so how do you determine and create these positional vectors?
Yeah, you're talking about like how the time in our EHR is imprecise. We do some rounding. So events that we don't have our imprecise time information for, we move to midnight, like 11:59 p.m. And then you will have multiple events at the same timestamp, and those will be handled. Those get handled naturally by transformers. Actually, you don't need to do any special handling for multiple events at the same timestamp.
Position embeddings are just days. They're in days offset from birth.
Yeah.
And sort of that assignment is the analog to a true positional encoding, which in a rotary embedding style is some offset from the beginning of the document. So in the text land, there is no notion of time that's represented as a token, right? And so that's the question, right? So yeah.
All right, we're at time, so thank you both Ethan and Jason for the wonderful. One question we couldn't get to online, I apologize, but we're gonna conclude the portion of this webinar. So